Hello! In this video, I'm going to talk about the question, what algebra rules do we need in order to be able to work with the quaternions? And as mathematicians, we want to be incredibly pedantic with this question. To assist with this pedantry, I've been working for the past many years on a Computation Assistant, which you tell it the rules and what rules you want to apply, and it applies those rules for you. It's halfway between a calculator, where you can feel confident in your answer, and working out by hand, which is good practice and keeps you in touch with the steps that you're taking. I hope it can also eventually be a good teaching tool for college algebra, making algebra a very tactile and explorable thing, but that's a long way off. So let's start with kind of a basic calculation that we might want to do with quaternions that will kind of show off most of the things that we'll be talking about in this video. Let's say we wanted to do 3 plus 2i times j minus 5k. Notice here we can move the mouse over and see the various pieces of this formula. Now, right now, there are no rules. So the rules are up here on the top right of the screen, and we have to add those rules in ourselves, and as we add those rules in, they become available to the system. If we want to deal with this particular formula, we need to do some foiling. And in particular, that consists of doing some distributivity both on the left and on the right. So let's actually start with right distributivity just to make this easier. So we can do some distributivity. And then, now normally you'd just be able to, if you wanted to distribute something in from the right, all you would have to do is use commutativity to move it over to the left, and then use left distributivity to distribute it in. But with quaternions, the order that you multiply things in matters, so we can't actually do that. We need both the right distributivity and the left distributivity rules in order to be able to work with something like this. So let's now take this 3 times j minus 5k, and let's distribute the 3 out. So we'll get 3j minus 3 times negative 5k. And then let's also, while we're at it, distribute out the 2i here. It's going to be a little bit more complicated. And let's just kind of work from left to right, trying to simplify this. We already have the 3j, and 3j is already simplified. That's fine. The 3 times negative 5k, this system, it doesn't work particularly well with negation, so I'm actually going to have to add in a new axiom that allows us to write. So this here is actually minus 5k, right? It's negative 5k as opposed to negative 5 times k, which we would really like the system to think about this as negative 5 times k so that we can associate that negative 5 out and multiply it by the 3. So I'm just going to add in a rule that allows me to do that. Here r is a special variable in the system that can only represent a real number, so we don't have to worry about, I guess you don't have to worry about anything going wrong here, but we just want to use this to turn the negative 5k into a negative 5 times k. And then we can, we need an associativity rule. So this is going to be x times y times z is equal to x times y times z. That's multiplicative associativity. So let's go in here. Oops, that's not what I want. There we go, multiplicative associativity. And now we have 3 times negative 5, which we need a rule for that. And this rule is actually a special rule. It's called calc. So this is just a real number calculation. And we can do 3 times negative 5 is negative 15. And then we can turn that back into a negative 15k. So that the system will turn it nicely into 3j minus 15k. But that's just an aesthetic thing. And actually we're going to have to turn that back later on when we want to combine like terms. Now we have the term 2i times j. And here, again, we're just going to want to apply multiplicative associativity to rewrite this as 2 times I times j. And then we're going to want to add in elements of the multiplication table. In this case, I'm just going to add in the ones that are actually important here. I times j is equal to k. That's a quaternion multiplication fact. Of course, we're going to need all of the basic quaternion multiplication facts from the multiplication table if we're going to want to do arbitrary quaternion math, but that's okay. For this problem, we only need a few basic quaternion multiplication facts, and so here we can turn I times j into k using that rule, and so now we have 2k. So let's work on this last piece. This last piece here is going to be a little bit trickier, but we can still do this. Again, we're going to want to turn this negative 5k into a negative 5 times k. There we go. And then we need to do some associativity. Our goal is to get that negative 5 and bring it out all the way to the front so it can multiply by the 2. And in order to do that, we're going to need to do some associativity. Let's see. There we go. And so now we have I times negative 5 next to each other on the inside. And there's actually a very useful fact. So multiplication of quaternions isn't commutative, but if we're multiplying a real number by a quaternion, that is going to be commutative. So we have the rule that Rx equals XR. Again, remember that R is a special variable that only represents real numbers. And this is going to be real multiplicative commutativity. So we're going to turn this I times negative 5 into negative 5 times I, and then we have to reassociate our formula to get the 2 and the minus 5 next to each other so that they can be multiplied by each other. Let's do that. 2 times negative 5, we're going to use calculation to turn that into a negative 10, and then we're going to do some associativity to turn it into negative 10 times I times k. We're going to need to know what I times k is. I times k is negative j, and to avoid having to do nonsense with negation, I'm going to want to say that I times k is equal to negative 1 times j, but that's the same. So that's going to be quaternion multiplication again, and we're going to do that, and then we need to get the negative 10 and the negative 1 next to each other so that we can apply our calculator to turn this into a 10j. So a lot of very complicated steps if you want to do this. We had this formula here, 2i times negative 5k, and we needed to do a whole bunch of really complicated associativity in order to get pieces next to each other that needed to be next to each other in order to apply various rules. For instance, we needed the I and the negative 5 to get next to each other so that we could switch them, and then we needed the 2 and the negative 5 to get next to each other so we could use the calculator rule. And again, when you're doing algebra, this is all very seamless, right? You don't think about the fact that you're using multiplicative associativity in order to get these pieces to be able to be combined with each other, and that's good. But it's always nice to sit back and actually think about and appreciate the fact that you're using multiplicative associativity. You're using associativity whenever you're doing these sorts of things. And speaking of associativity, we now have this expression here, and we're going to want to use associativity in order to turn it into one very long sum so that we can combine like terms. So what that's going to look like, I've implemented kind of a general additive associativity rule. So let's apply that, and it's just going to ask you what you want to turn this into, and it gets very unhappy if you tell it something that it can't be associated into. And so additive associativity is this kind of general principle that if you have two expressions that have a bunch of sums in them, that you can just kind of flatten out the parentheses. But you can actually break apart additive associativity into two separate rules. And it's just applications of those two basic rules. This system will actually show you what that breaking apart looks like. So we have kind of the basic binary additive associativity rule that x plus y plus z is equal to x plus y plus z. And then we also have some sort of rule that allows us to convert back and forth between binary forms where everything is associated to the left and polyadic forms where we're adding a whole bunch of things together. So in this case, it was able to turn the formula here, which was associated entirely to the left, it was able to turn that into kind of a form where it's just four things added together. But let's ignore that for now. We now want to do some additive commutativity. Additive commutativity, so again, you can break this apart into a just a binary commutativity that x plus y is equal to y plus x, and then what you have to do is you have to associate to get terms that you want to switch with each other into parentheses, switch them, unassociate, and then keep doing that to gradually switch the pieces of the sum to where you want them to go. So it's quite complicated if you want to actually write this in terms of just binary additive commutativity and all of our associativity rules, but you can do it, right? You don't need some sort of general additive commutativity rule. So let's apply, whoops, I need to actually add in the commutativity. This is going to be additive commutativity. And then I'm going to, my goal is to take the 10J and move it to the front so that I can combine it with the 3J. My next step is going to be to put parentheses back in using associativity so that I can combine like terms, and then I'm going to need to turn this negative 15 back into a negative 15k back into a negative 15 times k, so that I can combine these like terms. And you say, oh, do we need a special rule for combining like terms? Well, it turns out that we don't. You can use right distributivity. It turns out that distributivity and factoring out a common factor and combining like terms are all the same thing. So here, if we want to combine these like terms, we're going to use the right distributivity rule backwards. All of these rules apply not only forwards but also backwards. So we're going to apply this rule backwards to turn this into 3 plus 10 times j, and then of course calculate what 3 plus 10 is. Here, again, we want to factor out, undistribute that k on the right, and then we do negative 15 plus 2. You know how to calculate that. We're going to get negative 13k, and then we can turn that into a negative 13k so that everything works out nicely. Okay, and so with all of those steps, we were able to do this basic calculation, and here we had kind of a list of all of the rules that we needed to apply in order to get that to happen. Here we're just using binary distributivity, right? We're distributing values over a binary sum. But a quaternion, right, is the sum of four different things. And the way that this interactive thinks about the sum of four different things is very different from the way that it thinks about the sum of two different things. Of course, we as mathematicians, we can just use associativity to switch between one and the other, but the computer doesn't do that automatically. And so what happens when we want to, for instance, here I have, let's distribute a 3 over 2 plus I plus j plus k. And what rules do we need in order to be able to take that 3 and distribute it out over the sum of four things? One option is to just have a special rule for distributing out the sum of four things times the sum of four things, because that's really all that you're going to want. That's really all you're going to need in order to work with quaternions, because every quaternion we can reduce down to the sum of four things by combining like terms. And so you could have that, but it's actually, in terms of number of rules and whatever, we actually can handle these sorts of situations just with the rules that we already have. And the way it works is this. Suppose that we want to distribute this 3 over this sum. We need to use additive associativity in order to put a bunch of parentheses here and convert it into a bunch of binary sums. And then we can distribute the 3 over each of those binary sums. And then finally, we use associativity to kind of undo all of these parentheses that we've added at the very end to give us our answer. And of course, if we wanted to, we could calculate what 3 times 2 is. So that's how we can deal with if you have kind of a large distributivity problem, you can actually just deal with it as using associativity as a bunch of binary distributivity problems. Of course, you might also have the question, what if we wanted to add together 2 quaternions? So that's a thing that we can do as well. Here I have kind of all of the steps for adding together 1 plus 2i plus 3j plus 4k plus 5 plus 6i plus 7j plus 8k. And the way that we do this is exactly the same way that we did with, right, this is just combining like terms, the way that we combined like terms in our multiplication problem. We use associativity to kind of flatten everything out. We use commutativity to put the like terms that we want next to each other. We use associativity to put the parentheses around those terms. And then again, we use right distributivity. We distribute out that constant, the common I, j, and k in order to combine the like terms. Then we do our calculations and we get our answer. So these are the only rules that you need in order to be able to add arbitrary quaternions together, right? You need right distributivity in order to combine like terms. You need additive associativity in a very general sense. You need additive commutativity. Again, if you have additive associativity, you only really need x plus y is equal to y plus x, as opposed to some sort of more general principle of additive commutativity, where you can just shuffle things around however you want. And of course, you need real number calculation in order to actually be able to add the coefficients together. So we should start thinking about the question, if I have kind of a general formula involving quaternions, right? Maybe we were doing some really complicated calculation. How do I know what rules I need in order to deal with that much more general formula? I've talked about if we have the sum of 2 quaternions that are written out nicely, or if we're multiplying 2 quaternions. But what if we have some sort of formula that has like a bunch of sums and a bunch of products and all of that stuff kind of nested inside of each other? Well, our approach is actually going to be, and so this is not the approach that you would use as a human, but if you're trying to like prove what are all of the rules that we need, we're going to want to convert every formula that represents a quaternion into some sort of normal form. And that normal form is going to be a plus bi plus cj plus dk, where a, b, c, and d are real numbers. And I mean that explicitly, right? You can't just drop a term if the coefficient is 0. You have to write the coefficient of 0. You have to write coefficients of 1. You have to write coefficients of -1. You can't write subtraction. So our goal is to get an expression into this canonical form. And actually one of the things that that means is that we need to be able to get atomic expressions into this canonical form, right? We need to be able to turn, if you have an expression like j, we need to be able to turn that into canonical form, which looks like 0 plus 0i plus 1j plus 0k. Right, so that's going to be our canonical form for all of these quaternions. And in order to do that, we need a bunch of new rules. We need the left additive identity, and So you can either add in a right additive identity rule, or you can just use the fact that we have additive commutativity from before. Either one is fine. And then you need some additive associativity, because as you apply these additive identity rules, you get a bunch of parentheses that you don't want. So you use associativity to get rid of those parentheses. And then what we need to do is we need to use the multiplicative annihilator rule, right? It says 0 times anything is equal to 0, and we want to use that rule backwards to say that 0 is equal to 0 times anything. And so here we can rewrite this 0 as 0 times I, and this is 0 as 0 times k, and then of course we need a multiplicative identity rule to turn 1 times j, or we need to apply this rule backwards again to turn j into 1 times j to get everything into canonical form. And really these rules, you're going to want to use them actually when you're trying to do the reverse. When somebody gives you an expression like this and you want to kind of simplify that down into a nice form. But we're actually going to, in this proof, we're going to do this backwards, just because getting everything into a nice canonical form just makes everything a whole bunch easier. So let's say that we have some sort of expression, and here I've added in a special rule to do quaternion calculation to kind of assume that we just have all of the rules in place that allow us to add and multiply together two quaternions in canonical form to get a new quaternion in canonical form. So all of the rules that we have from previously, and then I also have some expansion rules from the previous page, and let's try, if you have some sort of expression like I times j plus 2k, suppose that you want to evaluate this expression here, right? So there's stuff going on. This is a nested expression. We have some multiplication inside of addition. And if you're dealing with an arbitrary expression, there could be lots of things going on, right? There could be addition inside of multiplication, inside of addition, and so on and so forth. But let's just see how we would deal with formulas in this form in order to get them into canonical form. So here I have I times j. I'm going to turn that I into 0 plus 1i plus 0j plus 0k. I'm going to turn the j into 0 plus 0i plus 1j plus 0k. And then we're going to multiply them together using the quaternion calculation rule. And then this 2k, I'm going to do exactly the same thing. I'm going to turn 2 into its quaternion canonical form, and k into its quaternion canonical form. I'm going to multiply them together using quaternion calculation. And then finally, I'm going to add together these two canonical forms using the calculation rules that we've established in previous slides. And what that's going to do is it's going to take this expression and it's going to, by applying all of these rules, it's going to get it into canonical form. And why do we care about canonical form? Well, really, if we're going to want to deal with quaternions, we don't just want to be able to do calculations with them. We also want to be able to, if we have two expressions that represent the same quaternion, we're going to want to be able to show that they represent the same quaternion. And by a series of applications of rules. So let me first go over all of the rules that we've kind of combined together and then show you what that looks like. So this list is complete in the sense that just having access to these rules allows you to do any sort of calculations that you might want to do with quaternions, assuming you're not trying to, do exponentiation or take reciprocals or things like that. But as long as you have some sort of thing involving sums and products and negation with quaternions, you can do a calculation just using all of these rules that I've listed out here. Of course, you're probably going to want a few more rules than that. This system right now isn't really designed for ease of use, and I'm hoping to be able to add a bunch more rules that will make it much easier to use without having to think a whole bunch about associativity in particular, because nobody wants to think about associativity too much. I finally want to mention what happens if we have two equalities, right? So here I have two expressions that represent the same quaternion. And so you might ask the question, by applying all of these rules, can I get from one expression to the other? And the answer is yes. And the way that we do this is we recursively work through the formula from the inside out, converting everything into this canonical form for quaternions. And at every stage, we know that our rules suffice in order to be able to, whenever we have a sum or a product, turn that into a thing of quaternions in canonical form. And so when we have these two, so we know that using these rules we can get from this expression to this expression here, which is equivalent and in canonical form now. And we also know that by applying these rules we can get from this expression to this canonical form. And then if you want to get from this expression on the left to this expression on the right, you just reverse this arrow. So one of the nice things about this system is that all of these rules are reversible. And what that means is we can turn this arrow around, and by applying rules we can get from here to this common canonical form, and then finally back to over here, to this form here. And so that allows us to, anytime we have two expressions involving quaternions, we can get from one to the other just by applying a series of rules. So thanks for following along with me. This approach of kind of taking a formula and working from the inside out, getting everything into canonical form, keeping track of all of the rules that you needed to use in order to get things into canonical form, and then keeping track of what you wanted to do with those canonical forms. This is a really important technique in model theory if you want to prove various axiomatizations. And in fact, I actually used a very similar technique in my PhD thesis to prove an axiomatization of a particular logical system. So this is actually really important from a logician's perspective. But unfortunately, it's not ideal from the perspective of usability. So ultimately, again, I want this interactive to be something that my students can use, my college algebra students can use and will want to use in order to be able to do algebra with. And unfortunately, the question there isn't so much what is kind of the minimal set of rules that you need to have, but rather what are all of the rules that you're going to want to have in order to be able to do algebra. And so my goal is to add in a bunch more rules, particularly rules, fancier rules that allow you to kind of ignore associativity. And so this is a long-term project, and a long-term goal of mine is to be able to produce something like this that allows users to play around with algebra. Computers are really great in terms of exploring visual things, exploring linear transformations, exploring the graphs of functions, exploring four dimensions. There's all sorts of very visual things that computers are great at doing, but I think that computers can also help communicate the ideas behind algebra as this sort of process that goes step by step, that has a bunch of rules, and there's this limited list of rules, limited list of things that you can do, and to kind of communicate and allow algebra to be explored. And so ultimately my goal is to produce a system that allows algebra to be explored in a very tactile way like this. But again, this is a long-term project, and I kind of wanted to show you what I have so far in this project. And so thank you for watching this video, and I hope to see you in future videos.